How's it going, everybody? My name's Ethan. We're going to do another video. This is going to be the part 2 for the motor controls that we started on the last video. And if you haven't seen that video yet, I'd highly encourage you to check that out first, because a lot of the content in this video is going to be a continuation of what we covered in that one. So be sure to check that out. I'll put a link up in the corner so that you can go back and see it. But otherwise, we're just going to continue. In this video, we're going to talk about speed control and how to do acceleration and deceleration of a motor in industrial process. Now, of course, there's many different ways to do motor process control, but this is going to be a pretty informative and educational video, and I hope that you'll stick around to the end to check it out. Anyway, let's go on and get started. So when we talk about speed control, there's a couple things we need to take care of before we proceed with controlling the speed of our motors. And the first thing we should do is get familiar with how our speed is going to be sent to the given motor. Now, in our case, our signal is coming from the analog card on the Point.io module that I showed you guys yesterday. So we can click on that module. Now, the majority of Rockwell's analog cards usually allow you to configure what are known as the engineering units of each channel. So if we go look at this particular configuration, the range in this case, this is a 0 to 10 volt analog card. So the output range in the module is 0 to 10 as it shows you. You can also change this to -10 to +10, but most of the time most devices can't handle that. It just depends on the type of analog device. But in our case, these two drives will take the 0 to 10 volts input, so that's what we'll use. Our engineering units can be pretty much anything we want. Now, certain cards will allow you to actually change the unit of measure for your engineering units. Like, let's say, for example, if we were speaking about rotation of an axis, we would probably use something like RPMs. So you could actually change the text to say 0 RPMs for low and let's say 45 RPMs for high. I kind of like keeping the values in standard integer numbers, since our analog output itself, if we go look at the output going directly to the card, this, as you can see, is indicated as an integer. And integers in the Rockwell software are just 16-bit words. And in older programming software like RSLogix 500, a lot of the time if you had a 16-bit word as your maximum, then your low would be 0, but then your high would be 32,767. And that would pretty much be the case for most of the analog inputs and outputs. So in keeping with tradition, I tend to go with that. It's a nice round number as far as binary is concerned, and it makes for simple scaling. So I've done the high as 32,767 and the low as 0. When you set the engineering units in your card, you typically also have output limits. Or clamps. These clamps will allow you to prevent the card from going above specific ranges. Let's say your 0 to 10 volts is this 0 to 32,767, but let's say that the maximum that the motor can safely go is 20% below full voltage. You could potentially do like let's say, for example, I used smaller motors that operated at like 6 volts rather than the 12 volt motors that I use right now. if I change my scaling, then it's still going to try to put out 12 volts for whatever my maximum scale is. So I can't really change the engineering units. And I can't change the output range, at least from the scaling part of the card. The only option we had was 0 to 10 or minus 10 to plus 10. So we can't really change that. So what we should do is clamp our minimum and maximum values so that they do not extend beyond the range that we consider safe for the drive. So if this is a 12 volt drive, then we would do half of 32,767. And remember, it's a binary integer, so no fraction. You just need to go to the nearest whole number. We could just do a quick little thing. 32,767 divided by 2 is 16,383. We obviously can't have fractions, so it would go to the nearest whole number, so it would be 16,384. That would be our max clamp, and that would clamp off our output at 6 volts, or half of our maximum output. And this would protect your physical hardware from an overvoltage scenario. So, with that out of the way, we can get out of that. And the first part about motor control, as far as speed, is we need to be able to scale our speed. So we talked about the scaling in the card, but obviously that's not the scaling of the real world. By keeping it in the program, it's easier to manipulate. So if the gearbox changes, or if we change motors to a different ratio, and they have a different maximum RPM at 12 volts, then we'll be able to just easily manipulate parameters in the program, and then the motor itself will not change. So a very common scaling technique would be a linear relationship scaling. So many of you who've been through high school may remember the formula y equals mx plus b, where y is your output, mx plus b is the slope formula for a linear slope graph. M times x, so x is our input, y is our output, and whatever x is multiplied by our scale. That creates a relationship that's linear, and then our plus b is our offset, because sometimes it may not necessarily cross 0. In our case it does, so our plus b is going to end up being 0 pretty much always. But in the event that our minimum value actually doesn't go to 0, then there would be an offset there. So in the program, we can just simply create an equation which will perform this operation internally. In RSLogix 500, if anybody that's watching this has used that before, we used to have a function called SCP. This was a function block which essentially did a linear equation internally. It was on its own a y equals mx plus b equation. You may remember an instruction called SCP, and SCP, or scale with parameter, is essentially just a y equals mx plus b instruction. You have an input, this would be your x value. You have your input min and max, an output min and max, and your output tag. The reason I am bringing this up is that in RSLogix 5000 and Studio 5000, the SCP function was removed. It does not exist in the 5000 series programming software. And I've heard many different reasons for why this is. The primary explanation that I've heard is that because scaling is handled in the card itself, that's why it wasn't added into RSLogix 5000, because the primary use for the SCP instruction was to scale your engineering units with your actual analog units to make it easier for that correlation. However, in my case, and I imagine many others, the SCP function wasn't just used for scaling the output card value. It was also used to scale various parameters or values within the program for various other logical operations. One thing that you can do in RSLogix 5000 is create your own instructions. One thing that I did was I created an SCP instruction for myself. So the SCP instruction is the exact same as what you would have found in the RSLogix 500 version of the software. It simply creates a y equals mx plus b value based on your inputs and your outputs. So you enter in your inputs min and max, your outputs min and max, and I made it a little bit more intelligent where I could add clamp values so I can pinch off the value in the software rather than having to do that within the card itself. It does a simple error calculation so we can prevent things like divided by 0 instances and anything like that. And then we do the little y equals mx plus b formula. The first thing we do is figure out what our slope is. And the next thing that we do is take that slope value and compute our output. Alrighty. So, as you can see, I went ahead and added the 2 SCP instructions for our speed reference calculation. And I've entered in our values. Now, the input and output min and max values and the clamp values could be associated with tags if we wanted to, but in this particular example it really doesn't make sense. We can just hard code those numbers in and it makes it a little bit easier and less tags to have to generate. So the motors that we have here, the indexer is 75 RPM at 12 volts. So that's the value for the input, 0 to 75. We remember our output was 0 to 32,767. Our min and max clamp is going to be the same, 0 to 32,767. If we need to clamp it, we can do that either here or in the card itself as we saw earlier. And then our output goes directly to the output reference that is mapped to the analog output for that card. So with this new instruction being done, we can now just simply delete that original rung, which was throwing numbers out there for each. And I've created 2 new tags, which are going to be our input value. This will be what comes into the calculation and get generated or converted to our actual output reference. So the next thing we can do is start creating logic that will start throwing numbers out there based on what we want to do. So let's talk about that part. What speeds do we need to be able to run at? Because our indexer runs at a higher RPM than our sorting table, we need to control that. If you remember in the video yesterday where we did the stall detection and everything like that, you notice that the in-feed indexer was moving significantly faster than the sorting table, and this is why. I had them both set to the same value, but that means that the indexer is always going to be higher speed than the sorting table. If we remember, I spoke about how it's easy to get marbles jammed inside the chute. With that being said, we obviously need to make sure that our sorting table is moving significantly faster than our in-feed indexer. Okay, so we're going to do a little bit of an experiment. The thing I want to do first is verify that our output matches what we expect it to be. So, given the specific motor's relative RPM and our scaling, I've set the program to just throw an output into the scaling logic that is exactly half of the RPM. And I did a little test on the computer before I came over here to validate that the integer value that we're giving out to the program, or that we're throwing out to the output card, is relatively the correct midpoint of 32,767. As we saw on the calculator, that's about 16,800 and whatever. And I have exactly that same number coming out of the scale. So as far as the SCP instruction is concerned, and as far as what's going out to the program, the actual output is half of 10 volts. So it should be about 5 volts. So I'm going to verify, for one, see what voltages we're getting out of the thing. So I'm going to check the analog output of the I/O card to see what our voltage is, and I'm also going to be checking the voltage that's coming out of the drive going directly into each of the motors to make sure it's relatively half of what we expect, the maximum being 12 volts, so the half should be 6 volts. So it should be relatively easy to see. So I'm going to go ahead and start it. Again, apologies for the noise today, but here we go. Okay, both motors are running. So the first thing we'll check, I have my multimeter already set to DC voltage, and we will just check it with the common on the output card. It's going to be hard to see what I'm doing, but you should be able to see the display on the multimeter. If not, I'll read it out just in case the glare is a problem. So we will put this here, and we want to check it against the common. So we look on the multimeter, it's showing almost exactly 5 volts on channel 0, and channel 1 is exactly the same thing as well. So as far as the output card is concerned, our output is exactly half of our 0 to 10 volts. So that's good for the program side of things. I'm happy with that. So the next thing we want to check is the voltage level going into each of the two motors. It should be half of the 12 volts, so that should be 6 volts going to both motors. So let's check that relative to what we saw. So to kind of sneak in here, and so we can see that the indexer is getting 4.3 volts, if I can keep the probe stuck on there. 4.35 volts or thereabout from the analog output of the drive. That's not exactly what we expect, but let's see if both motors are at the same set point. So down here we have a little connector. This is probably not great, but alright, so I don't know if you can see that, but the output voltage is showing 3.9 and some change. So for one, both of the drives are at slightly different values when they're both receiving the same input, and they're not exactly correct with what we expect. But that is also something else I haven't really tested, is validating that when I command 12 volts, for one, is it getting 12 volts? And for two, is that 12 volts equaling out to the relative RPM plus or minus a certain amount of tolerance to what I expect to see? There's a few things that we can take a look at. So I've turned the motors off for right now, but as you can see, these drives, these are the DC drives right here, they have a series of potentiometers along the top edge of them. Now, when I set these up, I initially had set the potentiometers to their highest level, but what may be happening is that our potentiometers are not exactly where they need to be, so their output is not exactly the same. As you can see, there's 5 potentiometers on here, and if we look at the manual, and I'll pull it up right here, the potentiometers that we have here control our maximum speed, and I also do believe there's a minimum speed set point, and there is an acceleration and a deceleration. The one that I am interested in seeing is what is our maximum speed set point. If it's not quite set all the way up, then I'll have to change that, because we don't really want to make the drive care about the output voltage. We want to be able to control that directly from the program. So it's not exactly what I wanted, but I played around with the potentiometers, but I got them to be exactly what we expect to see. So remember, the output voltage on the controller is still at 5 volts. And now if I check the motor, it's about 5.9, which is close. It's not perfect, but it's close enough. It's at least within a range that would be acceptable. So let me just check the bottom. So now it shows 5.9. So again, not perfect, but it's close enough. So it should be able to do what we want. The biggest thing that I'm curious of now is, after adjusting those potentiometers, is it actually following the analog speed reference, or did I somehow goof that by adjusting those potentiometers? So I'm going to change the speed on the computer real quick I'll just go up to full voltage and see if the rollers, or if the motors go up to that maximum speed, and if the voltage is actually what we expect to see. So as you can see here, I've just got the move instruction sending out a value. This is half of what we normally would see. I will just change this one to 75. We'll just do this one for right now. It sped up. It sounds like it's moving at full speed, but let's go check. So let's check this voltage. I've only changed the top one as I stated, so I'll just check it. And you can see it's exactly, or within a certain tolerance, 12 volts. So that seems right. This one is still at half. I'm going to change it to real quick, and then we'll check it. So as I said, I'm going to just change this one real quick. I'll just do a quick live edit. Maximum is 45, so we'll change that. It sounds like it has sped up. You probably see it there on the camera. Let's go check the voltage on that. Now that we've accelerated the sorting table, let's see what its voltage is. And that's 11.79. That's not exactly what we want, but if we remember, when we had it at half, it wasn't exactly at 5 either. Alright, so I think I'm just going to have to live with that. I tried to adjust the potentiometer again. It didn't really seem to let me go any higher than the 11.79 value. But it's close enough, and at half it was almost exactly 6 volts. So I think that it's adjusted in as good of a way as I can get it right now. I'll have to look and see if there's something else I can adjust. There could be something with that current limit that's keeping it from going any higher, and I may adjust that at a later time, but right now it's good enough for our relative speed experiment, so we'll leave that alone for now. I'm going to stop the motors. Okay, so now that we know that our relative speed is fairly accurate to what we expect, let's start finally discovering finding out what speed works the best with what we want to do. So the goal here is to take marbles from that indexer and fill them into the sorting table. So first of all, let's just set them back to roughly half, or well, in this case, exactly half So for this one it would be 37.5, and for the one down here we're going to change that to 22.5. That's roughly half, just because there's no reason it needs to run at full speed for what we're doing. I'm going to change that. Now, given their RPMs, we already know that the sorting indexer is going to end up being marginally faster than the outfeed sorting table. But let's go over there and check it out and see. Okay, so we're going to start it once again now that we have guaranteed that our relative speed is accurate, or at least our relative output voltage. Okay. So just visually, as we stated, it looks like the sorting table is at least a percentage slower than our indexer. I don't know if you can see it that well on camera, but they're almost not exactly correct. But we can, since we have a relatively similar scale value, let's set them both to the same RPM value and see what that looks like. So we'll change it to 22.5. Okay. And we'll just store that. So let's go back over there and see what our relative voltage or our relative speed looks like to see if they look very similar to each other. So with our new speed, we're going to turn this back on and see if both of the motors seem to move at relatively the same speed. Okay. I'm going to go with no. It does appear that the sorting table is moving marginally faster now than our in-feed table. Also, one thing that's potentially a little concerning, our indexer might be a little slow for our proximity sensor. We will probably have to adjust that timer, because I remember, if you remember yesterday, I set that to about 1 second, because the speed we were running at the time, it was making enough pulses within 1 second to reset the timer in a reasonable time frame. But now it's just probably barely reaching it, and I'll bet you if I just a little bit slow it down, it's still good, but a little too good. If this works with what we want as far as the action we want to occur, I may leave it alone, but we will have to see about that. It's right on the verge, so I may increase it maybe like 1/4 of a second or maybe 1/2 a second. Anyway, so what we're wanting to do is make sure that when we load marbles in, that we're moving within a reasonable enough speed to where the marbles will exit the indexer before they have a chance to jam. So even though the two motors aren't moving at the same relative speed, it's okay for this experiment. So I'll just throw one in there. So that came through, but one thing that was a little bit concerning, if you heard that little click, let's have another fall in there. That one was okay, but I think we were just in time. I think what's happening is that the table is turning a little bit too fast. So sometimes if the marbles aren't quite where they need to be, the marbles won't fall into the chute. So what we'll probably need to do is slow the turntable down just a tiny bit so that it has a little bit more time to catch up to the in-feed indexer. So I changed it down to 15, and just watching it myself from over here, it does look like that's still a little, well, it's slower, but it's probably too slow. So let's bring this up a little bit. This part of the process is more of just like trial and error, because ultimately we're just trying to find numbers that work best for what we're trying to do. Okay, let's go look at how that looks. So it's still faster, but not as fast as it was before. So we'll throw a marble in there. Okay. Now a real test would be to throw a couple marbles in there. Okay, so I brought out my little box of marbles. So a good test that I like to do is just throw a bunch in there and see, make sure that they get through the hopper okay. I have a big old box of these, and I'll probably end up getting more as the project continues, but let's just go ahead with this right now. So we'll just toss them in there. Okay, so I didn't experience any jam. So one thing that would happen is if the marble in the pocket, if it doesn't fall through fast enough, then what could happen is as the next marble comes around, it'll get jammed up inside that equipment. So that's the whole purpose of having the rotation detection there in the first place, because that can really cause issues. So let's do another little test. And again. Okay. So I'd hesitantly say that it's probably good. So as of right now, just from that series of tests, it doesn't look like that our speed is that bad. So I think that the speed set points that we have here are relatively good for what we want to do. So let's head back over to the computer, and we'll start talking about other kinds of speed control to go along with this. Alright, so now that we have determined our optimal operation speed, the next thing we want to do is be able to regulate this speed in a way that we can actually control our acceleration and deceleration. So the idea here is we could technically have the drive give us a ramp rate on its own. If you remember, there's a potentiometer on there that allows us to control the acceleration rate. And we could just leave it there. However, that kind of takes away some of our ability to do other kinds of speed control. And if anything else, the one thing it won't allow us to do is to directly control our acceleration. It's just all whatever the drive is set up to do. So by making it in the PLC, we can actually have more control as programmers. We can say, okay, well, half a second ramp up isn't quite good enough. Maybe we can just change it to a quarter of a second, or if it needs to be longer, we can make it a second. Whereas right now, it's currently based on a potentiometer where you're probably just going to have to eyeball it and hope it works. By doing it in the program, we can be a little bit more precise and know that our ramp rate is what we expect it to be. So the first thing we want to do is these values we've determined are good for our process. So this is what we're going to consider our automatic speed. So the first thing I want to do is, instead of these being hard-coded numbers, I want to change them to tags. And then what we're going to do is pretty much remove these two rungs entirely, and we'll actually handle this in our motor control, because there's some other things we'll have to do in addition to not only throwing numbers out there. We'll need to be able to calculate our ramp up and ramp down, and we will also need to disassociate our output for the relay in that interlocking logic that we showed on the last video. We'll have to disassociate that with our actual output, because what we actually are going to want to do is we don't want that relay to be open until our relative drive speed is below a certain threshold. So I'm going to make these into tags, and then we'll hop over and do the speed control. Alright, so I've went ahead and made the changes that I discussed a little while ago. I ended up doing quite a few changes, but what I decided to do was make the changes, and then I would just go over with you guys what changes were made, and we'll just cover those real quick. So the first thing that changed is we obviously, like I said, made the tag that would be our set point for the auto speed. So now we can just manipulate the speed to whatever we would like to run the line at least for this motor. And then over here we have two new tags that were also added, and this is our ramp up time and then our ramp down time, and these values are both in seconds. The other part that I had commented on doing is that we need to separate out or disassociate the conditions with our actual output, because when we open the relay we actually want to have already done our ramp down cycle. The only time that we would be willing to open the relay in that case is in the event of like an emergency situation where you need to pull power from the motor as soon as possible. The first thing we did was, rather than this logical interlock rung that we talked about, instead of that going directly to the relay, I've created a new tag that is called a logical forward enable, because that's essentially what it is. Logically, we are enabling this motor to move in the forward direction. I also added a new rung, which we didn't really talk about, but was kind of hinted at with this stop logic in the event that we have a fault on the motor for some kind of safety situation. So this is a safety interlock bit. If the safety interlock bit is lost, we will unlatch any running motor condition. And because it's a motor safety based input, we have it behind a delay. So the delay here is to ensure that all of the conditions have been met, and they have to have been met for a specific amount of time. In this case, 1 second, and then after that 1 second has passed, then we will energize the safety status enable bit. That just means that as far as the motor is concerned, everything that needs to be there is ready. So we have our control power, we have our safety circuit enabled, we don't have any faults, and we do have this drive supply power. Now, this is something I didn't mention that we had the last time. So one of the inputs that comes to the program is an input status about our 12 volt power supply when the power supply is active. This way we know that not only the drive's main breaker is on that supplies the 24 volt power supply, but also that the 24 volt power supply itself is on and supplying valid power. So assuming we have all of these conditions, our safety status is good to go after that delay. I added a new fault as well, and that's called this auxiliary fault. And what that is if we've commanded the relay to close but we do not see the status of that relay close, then we consider it to be a fault. And if any of these fault conditions come up, or the other two conditions, like I said, it'll drop out that bit. Now, I did a quick test of this, so I took the rotation detection off, but I'll remove that so that this rotation detection will function correctly. Also, while we're here, I will increase that timer delay to 2 seconds, because as we were seeing earlier in the video, that rotary disk wasn't spinning quite fast enough and was just about to be a issue for the fault reset, or for that timer delay. So the first thing that we have in our speed control is we want to throw our new value for our auto speed setting into what we call a buffer. And the buffer is going to be our theoretical speed set point, where we say, okay, this is what we need to look at. If we get a change in speed in this register, then we will either need to accelerate or decelerate. If we do not have the forward bit, we clear the value and it'll go to 0. The next thing we need to do is to know, are we accelerating? Are we decelerating? Have we reached the speed that we want? Or are we stopped? So that's what these bits do. So all this is doing is matching or comparing our buffer speed to this speed pre-out. So this speed pre-out is essentially what's going to get sent to the output value that will be scaled to go out to the program, or to the drive. The next part of the logic is where we actually calculate part of our speed accel and decel value, and this first one is called our scan rate. In case you're not familiar, the processor scans the program within a certain amount of time, and this is referred to as the scan time or scan interval. If you were ever curious, you can actually see your processor's scan time if you just pull this little submenu up in RSLogix and then put your mouse over the task file. You can also do it under the program files, but the task file is essentially your main program itself. So we can see that our typical scan time is around 2 milliseconds, and our maximum was 4 milliseconds. So what's going on here is we're actually looking at how much time has passed within that scan time, or within the last scan, and we can more accurately determine our ramp up time and ramp down time. When you're talking about something that's time sensitive, especially like ramp up and ramp down, you really want to have something a little bit more concrete. So this is based on the PLC's internal clock. There's another part of the program where we're generating this. So if we go into our background functions, I have it down here, and it's one of the last things. This is where the scan interval value comes from, and it's just a get system value of the time code, and we do a little bit of mathematical operations to see what the time was during the last scan versus the current scan, and then do a quick little subtraction, and we can calculate a value in milliseconds what our current scan time is for each scan interval. So we're taking that, we're taking the value that we want to achieve, or our final speed, we're calculating that against the scan interval, and we're also taking a look at our acceleration time set point. So then that gets taken down here, where depending on whether or not it's in accel mode or deceleration mode, it will just add to or subtract from the current preliminary speed value until we reach our buffer speed. Same thing for deceleration. We will keep subtracting until we reach our target speed. If we are at our target speed, then we stop doing subtraction and it just levels off. And then the second part of this is if we're going down and we reach below 0, well, obviously our speed can't be minus, so we will taper off our speed to 0. So that's what this clear instruction, if our value out is less than 0, then we just clear the value so it maintains that value of 0. And then the last thing we do in the program is we compare our output speed if it's above a specific threshold. So essentially it's over 2, then we will allow that relay to close. And we take that preliminary output and we throw it to the analog output card. So now that we've covered the program changes and how the logic works to control acceleration and deceleration, we can head over to the bench and make sure that our target acceleration and deceleration works and that our target speed is reached. Now, to make it a little bit more dramatic, I will change the automatic speed from 22.5 to, let's do the 45. And there is one thing with these drives, that if it's below 2 volts, it's basically 0. The drive will basically ignore anything from 0 to 2 volts and just not do anything. So again, we'll go over to the bench and see how that works out. Alright, so we're back at the bench. So I've only done the speed change to the in-feed indexer, so the sorting table itself is not going to start rotating, but right now for this part of the test it doesn't really matter. So we'll just focus on the in-feed indexer, and then we will copy the same logic over to the sorting table and just make it all work fine and dandy. So let's go ahead and do another start sequence. It's going to take a second to get through. So, as you can tell, it kind of did a little bit of a ramp up. Now, it was kind of fast, so what I'm going to do is I'm going to stop it again. So, you can tell it had a bit of a ramp down, so that's a little bit better of a ramp down than what it was doing before, where it would just open the relay and it would just come to a stop naturally. So I'm going to increase the ramp up and down time to about 5 seconds, so that way you can see that the ramp up and ramp down are able to change more controlled. So I'm going to change that real quick. Alright, so I'm going to change the ramp time to 5 seconds, and I'm going to change the ramp down. Let's actually go crazy and say 10 seconds. One other thing I'd like to do, that rotation detection, if you remember I said something about the drive really won't detect any speed rate less than 2 volts. It just basically ignores that. So one thing we want to do is this rotation detection. We want to make sure that it does not get triggered when we actually don't have a speed fast enough to care or to actually do anything to the drive. So we are going to add a compare instruction to this. We're going to put a greater than instruction here, and what we're going to look at is, we'll go down to the bottom, and we're going to use our actual speed. So I'll just do a copy. It's actually going to copy the whole thing, not just the one tag, but it's fine for what we're doing. I just pull what I want and then delete the thing. So we'll take this, delete that, and we want to look at it if our output is greater then what would equal out to 2 volts? I don't know what that is offhand as far as our actual speed, so I'm just going to give it a set point of 5. I'm also going to increase the delay to 5 seconds, at least for now. I'm going to do a calculation in a little bit, probably off camera, and get it to just over what the 2 volt value would be, and then I'll just put that there. So I'm going to just leave it this way for now. It's not really that critical at this moment because right now I'm not putting any marbles in it, so we won't really be bothered by it too much. But anyway, let's head back over there and run it again. Alright, so let's do a little start. Alright, and I don't know if you can hear it on camera, but in my ears I can actually hear it when it's ramping up. There's a little bit of a high-pitched, high-frequency squeal as the current increases. So that at least tells me that it is starting to send a command, and then as it ramps up it changes speed. So as you can see, we ramped up. It was about 5 seconds. So then we'll do the turn off, or the ramp down, which is going to take much longer because we set it to 10 seconds. So all right. Now you noticed that the relay didn't click off immediately, but the speed completely stopped on the drive. Now, again, that illustrates the thing I was talking about earlier. When our voltage dropped below that 2 volts, the motor stopped because the drive stopped sending anything out. But the relay didn't click off because in the program, our speed had not reached that 0.2 volt value, or the 0.2 RPM. But that just demonstrates the ramp up and ramp down of the project. Now, like I said, what I'm going to do is incorporate the same thing into the sorting table, and it'll essentially do the same thing, but the focus of the video was primarily to just talk to you about the ramp up and ramp down. Alright, so that was the video on speed control and how to do acceleration and deceleration in a controlled manner. I know there was a bit of a convoluted mess with this video, and I apologize for that, but I kind of think that it's nice for you guys to see not just the programming side of things, but also to understand the physical part of it, you know, how it relates to physical machinery in the real world. And of course, this is a scale model of, you know, it's not even really a true process machine, but it helps to illustrate a lot of the things that you might come across in industry and ways that you can figure out to control your process, whatever that may be. So I hope you guys enjoyed this video. I know it's a little bit different from what I've done so far, but it's a nice addition to the video from the last episode that we did. Hopefully you found that educational and informative, and if you did, I would kindly like a big thumbs up if you don't mind, or if you didn't like it, you can give me a thumbs down too. It'll help me understand what kind of content you guys like to see. Also, if you have any questions regarding what you've seen, or questions regarding the programming, or anything else that you want, or if you have suggestions for future videos, I'd really love to hear from you, and so you can put something down in the comments, if nothing else, just to say hello. If you like videos like this and you want to see more, be sure to hit the subscribe button and click the little bell icon so you'll be notified when more videos come out. I'm going to try to start sticking to more of a once a week thing. I've done a lot of videos this week and I understand that, but the main thing was that I had some content out there, not just like one video and then waiting. I may do more of the rapid fire videos where I do like multiple in a week if I can, especially for like in the event that I know that I've got a trip coming up. But otherwise, I'm going to just keep going at a once a week thing if I can, at the very least. Anyway, I think that's going to do it for today, you guys. I hope you guys have a great week, and I will look forward to seeing you on the next video. Anyway, thanks again, guys. Bye.